So here we're going to look at how to solve some projectile motion problems. First of all, what is projectile motion? Well, a projectile is any object that is just subject to gravity as it moves through the air. So for example, in this image, soccer ball, this person here kicks a soccer ball, and while the soccer ball is in the air, it follows this path, and that is called projectile motion. The shape of the path might look familiar to you, and actually the shape that a projectile makes is a parabola. It's a quadratic relation. So that's one of the reasons we learn about quadratics in math class, is because we see them all the time in physics. So projectile motion are objects that are experiencing this type of motion, falling through the air, and we're going to solve some problems with that today. First, few things to notice. The ball is kicked here, and it lands here. We call this distance, while it's in the air, we call that the range of the ball, or of the projectile. Okay, so that's the distance between here and here. And then other important things that we need to know, the maximum height, that's something we're often trying to find. So that's the maximum height the object is off the ground. And then also you might hear it called hang time. Hang time. And that is the length of time that the ball is in the air. So it's basically the length of time it takes for the ball to cover the whole range, right? So those are sort of just some of the terms we're going to use when we're talking about projectile motion. Let's go to a problem. So we're going to skip this table for a second. We're going to come back to that. But let's go straight to a problem. An object is projected horizontally from the top of a cliff. How far from the base of the cliff will the object strike the ground? So let's draw a cliff. Let's assume it sort of goes straight down like that. And then the bottom of the cliff like that. So we have an object that is projected horizontally. So if it starts up here, let's just draw it like a ball. It's projected horizontally. It's probably going to follow some sort of path like that, right? We can assume it looks something like that. It's sort of like half a parabola in this case. So we want to know how far from the base of the cliff the object will strike the ground. So we can call that this. So that's basically this distance here, right? This is what we're looking for. We can call that the delta D that we're trying to look for in this question. And what else do we know? Well, we know that the ball is projected at 8 meters per second. So at the top of its flight, the initial velocity of the ball is 8 meters per second. Okay, so how do we analyze this? Oh, and also, sorry, one more thing. We know the delta D in the length of the cliff, or the height of the cliff, we know that is 122.5 meters, right? So we know this. And in order to solve problems like this, our strategy is always the same. Just like we did with relative motion problems, we break up the x component of the motion and the y component of the motion. And we look at those two things completely separately. So let's look at the x motion first. Let's look at the x direction. Oops, let's do that in red. I'm going to do all the x direction in red and the y direction in blue, just to try to organize ourselves here. So this is in the x direction. So the thing is, in the x direction, initially we have a velocity of 8 meters per second. And the question is, as this ball falls, so when the ball's here, does that horizontal velocity of 8 meters per second change? Well, remember, in order to change a velocity, we need to apply a force to the object, right? To apply an acceleration, which changes the velocity. But is there any force in this xward direction? And the answer is no. There's no force in this x direction. In fact, if we looked at this ball, just a free body diagram, I'm just going to off to the side do a FBD of this ball. As it's in the air, literally the only force that's applied to it is the force of gravity. It does have horizontal speed, but there's nothing pulling it in that horizontal direction or accelerating it in that horizontal direction. So in the horizontal direction, that 8 meters per second shouldn't change. So at this point here, the ball is still experiencing a v, or a speed of 8 meters per second, right? Even when it's down here. Let's be consistent about the color of the ball. even when we're down here, the velocity of the ball should still be 8 meters per second because there's nothing to change that velocity, right? So in the x direction, we have a constant velocity of 8 meters per second. So that's cool because we're trying to find this delta d, this change in x direction. And in fact, if we wanted to keep ourselves a little more organized, I can call this delta dx. This is the x direction displacement. So if we think about it, the ball has just moved to the right at a speed of 8 meters per second. Yes, it's also moved down, but we don't worry about that. We just worry about the fact that it's moved over by 8 meters per second. Oh, sorry, at a speed of 8 meters per second. But can we figure out this delta dx? Well, we know a constant speed, but we do not know how long it travels in this horizontal direction. If we knew it was like 1 second, for example, we know it would travel 8 meters. If it was 2 seconds, it would travel 16 meters in this direction. But we don't know the time yet. And we can't really do anything else with this x direction of the motion, the x component of the motion. So let's start looking at the y component to the motion. In the y direction, what is this object doing? Well, notice how it starts off moving completely horizontally. So that means, what's the vertical velocity at the beginning? Nothing, 0. It's not moving vertically, but as it falls, it's going to pick up some vertical velocity, right? And as it falls farther and farther, the vertical velocity is going to be greater and greater. So this is essentially the same motion as a ball that was just dropped from a height of 122.5 meters. So it's almost as if you just took a ball and you dropped it, and it gets faster and faster as it falls, that 122.5 meters. So that's essentially what we do to look at the y direction or y component of a projectile, is that it's accelerated downwards at a rate we know, right, very well, is 9.81 meters per second squared. So if I draw a squiggly line to represent the acceleration, this is 9.81 meters per second squared, right? That is the acceleration of the ball. And we know that based on the free body diagram, it's just pulled directly downwards, okay? So we basically changed the question into just a ball being dropped. So if we think about what we have, we know our VI is 0. We know our acceleration is negative 9.81 meters per second squared, right? If we consider the upward direction positive. We know our delta D, or our change in y direction, we call the delta dy if we want, is negative 122.5 meters up, right? We could also have defined positive as down, but I'm just going to keep it negative down to keep it consistent. So we know these three things. What can we find using this? Well, remember, for this part, we're trying to find the x component here, right? How far it's traveled horizontally. But in order to do that, we needed the time, how long the ball was in the air. We can find that time from the y component. So we're looking for delta t. That's the thing we don't know. So if we look at our 5 equations of accelerated motion, remember this is accelerated motion because the object is falling directly down due to gravity. The equation that we can use is delta d equals vi delta t plus 1/2 a delta t squared, right? With the vectors in the proper places. We know our initial velocity is 0, so that's going to go to 0. And we can just solve for t. T is just going to be equal to the square root of delta d over, or 2 delta d over a, right? If we calculate that. And if you do that calculation, I encourage you to actually do the calculation. Pause it here if you want. Do the calculation. It comes out to 5.00 seconds. So that means it would take a ball 5 seconds to fall from here down to the ground, which actually is the same time it would take a ball from here, even if it's launched horizontally, to get to the ground because it didn't start with any vertical velocity. So that 5 seconds we can now use because we know that it traveled horizontally for 5 seconds as well as vertically for 5 seconds, right? Because it hits the ground in the vertical direction at the same time it does in the horizontal direction. So in the x direction, we know that it travels for 5 seconds. So we can just we just know that v, an average speed, is equal to delta d over delta t, or our change in displacement or our change in position is v delta t. So we can just multiply 8 times 5 seconds, which is 40 meters. That's it. So the ball travels horizontally, or the object, I should say, travels horizontally 40 meters from the top of that cliff. So again, we looked at the vertical motion, which was accelerated motion, and we looked at the x direction, which was not accelerated because nothing was pulling it in that direction. So that was just uniform motion. So just to quickly summarize, the vertical motion of projectiles is always going to be accelerated. And the horizontal motion is always going to be uniform, or constant velocity, right? The equations to describe the motion, we know for accelerated motion we have the 5 equations. And for uniform motion, we have our definition of velocity, which is delta d over delta t, right? And we'll put arrows over those things. We can use our vertical motion to find the time, right? The time that the ball is in the air. Really, we can use it to find the max height, because the height is vertical, up and down, right? We can use the horizontal motion to find things like the range, so how far the ball goes, and yeah, other little things that you'll see when we do some more questions. But those are basically the things that we can find using those things. So let's do one more question together. Question 2. An arrow is shot at a 30-degree angle at the horizontal. It has a velocity of 49 meters per second. How high will it go? What horizontal distance will it travel before it hits the ground? So let's draw the ground down here. We'll assume the ground is flat in this case. In most questions it is, unless it says specifically that it's launched from a certain height or something like that. But let's assume here that it's launched from the ground level. It is launched at an angle. So let's assume that's our arrow as it's shot. It's launched at an angle of 30 degrees. And the path this thing is going to follow is going to be something along the lines of that, right? It's going to follow that parabolic arch, and the arrow is going to land somewhere over here, right? So the question is, we know we're going to have to break this up into the x component and the y component, right? We want to know the height that the arrow goes, right? So we want to know this height, and we want to know the distance or the range, and we can call that delta d in the x direction, right? How far it'll travel in the x direction. So how do we find these things? Well, again, we have to break it up into the components of motion, the x component and the y component. Unfortunately, we were only given an initial velocity in terms of an angle, 30 degrees, and it was 49 meters per second, right, at that angle. Luckily, we've covered in this course how you can find the components of a vector. We can break this vector down, if this is 30 degrees here. I'm just zooming in sort of on this right here. If this is 30 degrees here, can we find the x and the y components of it? Well, the components of it look like this. The x component is like this. The y component is like this. So if we call this v1, or our initial velocity, vi, we can call this one vi in the x direction, and we can call this one vi in the y direction. And we can just use a little bit of geometry to find out what those two components are. So v1x is just going to equal 49 meters per second cos 30 degrees, right? Because cos is the adjacent side. And if we do that on here, we get that the x component is 42.44 meters per second. I'm going to keep it 4 significant digits. We can round at the end. Okay, so this component of it is 42.44. So in the x direction, basically the initial speed in the x direction is 42.44 meters per second. And we can find the initial speed in the y direction, which is going to be 49 meters per second sine 30 degrees, which is ooh, I should be able to do this one in my head. It is just 24.5. It's just half of the initial velocity, meters per second. So we see right away this object has more horizontal velocity than vertical velocity. So we expect it to go pretty far horizontally, but not necessarily as high, right? So now that we know the different components, we can look at the different parts of the motion. So first of all, we want to know how high this thing's going to go. So part A asks us that. So we can think about this as one of our old problems. We've done a million problems like this. A ball is launched straight up with an initial velocity. How high does it go? And that's basically the same thing we're doing here. We're looking at a ball or an arrow that's launched upwards with an initial velocity of 24.5 meters per second. How high would it go? So let's start with the Y motion. Okay, so in the Y direction, we know our initial velocity, our starting velocity upwards is 24.5 meters per second. And we know, obviously, our acceleration is negative 9.81 meters per second squared. And these are, by the way, both in terms of up as our positive direction. What else do we know? Well, if we're thinking of this problem as just an object that's sort of thrown straight up and then comes straight back down with an initial velocity 24.5, at the maximum height, what do you know about that object? We should be able to figure out what our final velocity is. It's going to be 0, right? It's going to be stopped. Whenever an object is thrown straight up in the air, it stops at the top, right? And we're trying to find our delta D, and we'll call this delta dy because it's in the Y direction. That's what we don't know. So which equation can we use for this? Well, we don't really care about time, right? Time is the thing that we don't care about. So we can use, which equation is this? Oh, we can use this one. The one that is F squared equals VI squared plus 2A delta D. Right? We can use that one, and we're solving for delta D. So to rearrange this, it's going to be VF squared minus VI squared all over 2A is equal to delta D. So if you plug everything in and you simplify it and evaluate it, which you should pause the video and try here, you get about 30.6 meters. I don't know why the answer here says 32. Maybe that's rounding error, but it should be about 30.6 meters, or about 31 meters. If we stay consistent with our significant digits, it should be about 31 meters, because our initial velocity only had 2 significant digits. So here we go, 31 meters. So it basically goes 31 meters upwards before it falls back down. So that is our maximum height, which we have found. Okay, so I'm going to label this because the question here isn't separated by A and B. I'm going to say this is the max height, just so it's clear. Okay, now we want to find the range of this projectile, or how far it goes. And there's actually a few different ways to do this. But when we're looking at the range, we're looking at the x component of the motion, right? Like how far it goes this way. Unfortunately, so we know also that in the x direction, the speed is 42.44 meters per second. Is that ever going to change? Well, there's nothing pulling it in the x direction after it's launched, right? So we can assume that we're just, in the x direction, we're just experiencing a constant velocity of 42.44 meters per second. So if we know how long it's in the air, we can just multiply by the time by that in order to get our answer. So in order to do that, though, we need to know how long it's in the air. So there's actually a few different ways to find the time that the object is in the air. So one way you can do it is if you realize that this is a parabola that's symmetrical, you can find out how long it takes the ball to get to its maximum height using one of the other 5 equations and the y direction. We're dealing with the y direction still because that's how we find our time. And then once you have half the time, you can just multiply it by 2 to find out how long the rest of the time is. So that's one way to do it. There is a more direct way to do it, and that is by using another one of our equations of motion. Think about what we know. So this is we're still looking at the y direction because the y direction will tell us how long the ball takes to get like from the bottom to the top and back down again. Because what we know is we know the initial velocity is 24.5 meters per second. We know the acceleration is negative 9.81 meters per second squared. We know, well, another thing we know is that when the ball goes straight up and straight down, gets to the top and then comes back down, it ends up in the same spot that it started. So basically what we can think about is that the delta D is 0 between the starting point and the ending point. Remember, the delta D is the displacement, not the distance traveled. It's the total displacement. We'll put an arrow over it to signify that. So we know the displacement is 0. How much time has gone by to find how much time has gone by to make the displacement 0. That's what we're trying to find. So if we look for the equation that has this stuff in it, notice how we don't care about our final velocity here, though you can figure out what your final velocity is as well. But let's not worry about that right now. So the equation that we can use is delta D equals VI delta T plus 1/2 A delta T squared. So if we plug everything in, our delta D is 0, right? So that's going to be 0 in this case. But can we simplify this equation for T? Not really, because there's 2 of them, right? And one of them is squared. So we sort of just have to plug in what we know. 24.5 delta T plus 1/2 times negative 9.81 delta T squared. What kind of equation is this? It is a quadratic equation, right, that we have to solve. So we can start off by making it a little bit simpler. We can put it in our ascending order of degrees. So 1/2 times 9.81. So our first term is going to be negative 4.905 delta T squared plus 24.5 delta T. So this is a quadratic equation. You can solve it in whatever way you want. You can actually factor it and solve directly. Or what I'm going to do is I'm just going to plug it into the solving mode on my calculator, which can solve quadratics for me. You should be comfortable with both methods of doing it, either factoring and solving it or using your calculator. So try it your own way. Pause the video here and see what you get. So when you do that, your two VT values that could be the answers is 0 seconds or 4.994 seconds, basically 5.0 seconds. Those are your two answers. Do these answers make sense? Why is one of the answers 0? Well, if you think about it, it makes sense because at time 0, your ball's on the ground. The displacement is 0, or your arrow's on the ground. And then it goes up, it comes back down. At time 5, it is on the ground again. So those are our two answers, 0 and 5 seconds. And that refers to this point here and this point here. So it makes sense that there are two of them. So now that we know the arrow is in the air for 5 seconds, we can switch to our X motion. Oops, wrong color. We can switch to our X motion, right? Because our X motion is what we use to find the distance. And we know that the delta D is just going to be the average speed times our time. In this case, our average speed is 42.44 meters per second in the X direction times 5 seconds, which gives us 212.2 meters, or rounding to two significant figures, about 210 meters. Which, again on here, the answer here is a little bit off, I think, due to rounding. Should be 210 meters, not 220 meters. So there we go. And then let's label this with, this is the range of the projectile. Okay, so look at what we did here. We used the y component to find out how high the ball went and how long the ball was in the air. I keep saying ball, but it's an arrow. You get the idea. And then we use the X motion to find out the range, how far it traveled in the X direction. Okay? There we go. There are projectile motion problems. It's about breaking it up into the X and the Y component of the motion.